Welcome back, boys. I think we were looking at having a look at the inorganic polymers. In under this section, we shall see some more today. That is the next part of that syllabus. It contains something which we call as silicones. We are already aware of the silicates that has a structure of SiO4, and it almost is a tetrahedra like a silicon at the center and uh, four oxygen atoms at the different corners of the tetrahedron. O minus 1 is at the center, which is at the backwards. So you'll have 4 minus, and this thing is a silicate. If you want to have a polymer, it can go on like this, and it can exist like this. So this will be linked by oxygen atoms here. So it can go on like this. But with silicones, you'll have something like SiO, Si, and this will be connected by means of some alkyl groups. Okay, and this Si will be replaced. Here you got SiO, and then you can have another Si link there, but it will be replaced by H here. And these are the macromolecules that contain elements other than carbon as part of this principal backbone structure. This is an important point you need to remember. And you can find them in mica, clays, and talc, etc. I think you know about mica that we use exclusively in the carpentry work and clays, etc. But they have got different substituents where you can use R equal to CS3, and you know very well you can go for C2H5 and some CnH2 N minus 1, like that it can go on. So the typical examples include silicones, silicates, zeolites. This is a separate kind of polymer which we are going to see, and phosphosines also is there. So let us look into the synthetic organosilicon polymers that contains repeated SiO R2 SiO units held together by SiO-Si linkages. So here is that silicon there. So here, this, if you put something like bracket, this is the repeated, getting repeated in times, and in one terminal you will have H, the other terminal you will have OH. This is what you call it as the silicones. Of course, there are a lot of applications. I'm going to tell a few about them. And the beauty with this is they form straight chain and cyclic forms are possible. Straight chain just go on like this, and then cyclic forms like the one which we find in the silicate cyclic forms. So chain growth may be regulated using by adding CS3 thrice SiCN during hydrolysis. This is a process that is connected here. And hydrolysis of alkyl trichlorosilane gives complex cross-linked polymers. This is an essential point there. And you can see that here you have got 2RCl. So let us just take this as R equal to 2CS3Cl plus Si will give you CS3 twice and SiCl2. So that is, you can record this temperature at 573 degree Kelvin in the presence of copper catalyst as a powder which enhances the reaction. You get this silicon chloride, silicon dichloride. So in the same temperature and the same reaction mixture, it is made to react with water, forming silanol. So what has happened there? Two chlorine atoms have been replaced by two hydroxyl groups. So this is just a perhaps kind of nucleophilic substitution there. Now you can have NR2 silanols, that this is it, called as the silanol. OL means you have got alcohol. With further reaction where you get condensation reaction, but still in the presence of water it takes place, and here you can see that water is removed in the presence of water. So this is kind of a careful industrial reaction to give something like SiR2. Both the R2 is retained there. Here you got one R, this one is another R, and this one is another R. Silicon is retained there. Silicon comes there as it is, right? And you have two OH2 there. That is the OH are twice. So let's see what has happened to that. That OH is also here and this OH is also there. But what has happened here is it is getting repeated. It is getting connected. So it will go something like SiO, and even then the next will be SiO, next will be SiO. It keeps on repeating. The last part you will have OH, and this first part you will have OH there. So you will have so many SiO bonds. And there is also possibility that you can have this R as a substitution there. And you can have R equal to CS3, C2H5, etc. And even you can have OCS3, or even you can have OCF2S3. It depends what properties you need, and you have to just prepare and find out which one is very suitable for what kind of property there. Sometimes you get gel-like substances, sometimes you get liquid substances, sometimes you get solid substances, and that depends on the entire R that you get substitute there. Okay, and here is the property that we have come across. That is chemically inert. It doesn't react at all. It likes this like sand, and it's a water repellent, resistant to heat, and the chemicals and oxidation that is also resistant to chemical and even resistant to oxidation because of the high SiC. I think this SiC is kind of a carborundum. It is highly used in lathe tools, okay, where the temperature doesn't reduce that substance. So it's that kind of bond there. So silicon fluids are used as lubricants and in anti-foam agents, and greases, and high temperature oil bath, vacuum pump, etc. And silicon rubbers are resistant to weathering. Weathering means tear or long temperature. So that is a kind of high substitute thermal efficiency. I think you know what is this foam and the kind of all thermal resistant materials such as the thermocool that we call all made up like this. And it has got low flow resistance and is used in gaskets in the cooker, pressure cooker. You have that gasket that doesn't allow the escape of the gas, and seals, insulation, containers, surgical devices. So a lot of details is is industrial one. Details are with industry. Therefore, it comes under industrial chemistry, which has got a production that is large, that is based on large scale production, and that has got a different kind of chemistry. And then the last thing is you can use them as a silicone resins, insulating coatings, and varnishes. Then you have the silicone fluids, straight chain polymers plus cyclic chain polymers. These fluids have a special property of about that kind of polymers, and they have got a varying boiling point and viscosity. So it's a high temperature, low flow. At places where you require, you can just use. So they contain about 20 to 25, 20 to 500 units. So N equal to N. Remember this SiO, Si, N. So that particular N will come to around 20 to 50 there. So then you have elastomer, which has got some good elasticity, or silicone rubbers. You might have seen several places that silicone rubbers and silicone. So they are the linear polymers. Straight chain polymers is different from cyclic polymers, is different from linear polymers. In a straight chain, you will have something like CS3. This is a straight chain. Okay, so this is straight chain. There is no branching at all. Then you call it as a linear polymer. So linear polymer is a fallout of the straight chain polymer. But in some cases, what you do is the straight chain is substituted by some R groups, which gives rise to nonlinear polymers and also the cyclic polymers. So both are almost the same, but here they should have a linear property. That contains about 6,000 to 6 lakhs silicon units. So more number of units per polymer. And then you have resins, which stands the tear and wear. So very stable thing. So that is called cross-linked polymers and hard and stiffer than rubber. So we are not going to look much into the details of these things, but anyway, I'll just write the uh, properties of this thing here. Just a minute. So you can see that the silicons are different from many industrial polymers, and this is the write-up that I was just was willing to give you. Different in many industrial processes where the chain of atoms that build the backbones of their molecules does not include carbon. So without carbon, this goes without carbon, right? So this is the write-up, and so maximum number of class 2 organic groups such as methyl, vinyl are linked to every silicon atom. That is the R. The general formula of silicon is R2SiO(X), where R belongs to any of the groups. Then Poly-dimethylsiloxane is the most widely used silicone compound which can illustrate the primary characteristics of the organic class. The first substance is the metallic silicon obtained from the silica sand, that is this one. Okay, and the silicon reacts with methyl chloride. This reaction you have seen and forms a dimethylsiloxane over a copper catalyst. So this reaction you have seen there. When the compound is made to react with water, the atoms of chlorine gets replaced by hydroxyl group. The resulting compounds silanol and polymers in reconciliation reactions every individual unit of the molecule there. So applications part, there are a lot of the application parts there, and here is what the major difference you have to write. When you have this 2CS3 only, you call it as the silanol. When you have 2CS3, another CS3, and this another R, then this an alkoxis again. And then when this OR is substituted by one vinyl group, this is called as a vinyl silane. This is the major widely used sealants there. And these oligomers and monomers, oligomers more than one, monomers can further be modified to produce large number of products such as room temperature moisture curing silicone rubbers. Moisture is one of the great culprit for destroying many things, and I think you can see in many electronic boxes you will have silicone balls. So like that, then silicone adhesives, coatings, sealants, and caulks are used. In the silicones are used. So it's a remarkable and versatile. Versatile means very wide, and because some of the substituents that are there, it's alkoxy, amine, oxime, and acetoxy there. So you can see that alkoxy has OH, R2NH, R2NOH, R2COH, some important derivatives of the silanes, and these change the property of the silicones. So that comes to that. So you can find the description in the notes section. Thank you for joining me. We'll see you soon.